class. This is going to be a lecture that will finish up 11.4 and 11.5. So hopefully you will work through this set of material and make sure you ask if there are questions. Here's where we ended class last time. We were talking about colligative properties, and we had claimed that for every colligative property there are 4: vapor pressure lowering, freezing point depression, boiling point elevation, and osmosis. For every one of those, and only for those, you will have to talk about effective concentration when you are trying to determine the actual values for those colligative properties. We defined effective concentration as being the normal concentration multiplied by a factor which we'll call lowercase I. I is a 1 if you're talking about a covalent compound, since they dissolve as one molecule, but I is the number of ions that separate if it's a strong electrolyte, because those make ions, and we practice counting who does that and how many ions they make. So, for instance, let's say that we have an example, and we want to say, rank the osmotic pressures for the following. Let's say we need to consider 0.040 molarity CH3OH, 0.025 molarity NH4NO3, and 0.030 molarity strontium iodide. All of these solutions are aqueous, they're in water. And we know that if we want to rank osmotic pressure is pi equals m times r times t. But I'm saying that instead of using the m value directly, you will have to use an effective concentration that multiplies these by the appropriate factor. Whoever has the largest m will have the highest osmotic pressure. Lower m's would be lower. Well, this substance right here starts with not a metal, and it's not NH4, so it's a covalent compound. It is molecular. Its effective concentration is 0.040, just like it says right there. This one, on the other hand, does start with NH4, which makes it be an ionic compound that's soluble. Therefore, it separates, and it separates into 2 ions. It makes both NH4 plus and NO3 minus. Those are 2 separate pieces. There are 2 ions, so you multiply by 2, and that is 0.050 molarity. Over here, strontium is a metal, so this separates into 1 piece of strontium 2 plus and 2 individual pieces of I minus. Well, that's 3 pieces of ions, 1, 2, 3, which means this effective concentration is 0.090 molarity. Now that we have effective concentrations, effective molarities, we can rank them. Highest molarity is going to be highest osmotic pressure. That would be this one. This is highest. The next highest is this one. Next osmotic pressure. And the lowest is this one. You're required to do that without being asked. Only for colligative properties, and always for colligative properties. So you'll always need to be thinking for an aqueous solution, is it a strong electrolyte, or is it covalent? Is it molecular? You can also use this for number calculations. You should have your own periodic table. You should have the Chapter 11 handout, so make sure you have them so you can look at them. Here's question number 11. A solution is made of 0.10 moles of Na3PO4, and they put it in 525 grams of H2O. And then the question asks, what is the freezing point? Well, freezing point is a colligative property. Freezing point is lowered. There's only one equation for this. The equation is delta T of freezing equals K of freezing times molality. But now we'll have to make an effective molality. So we can do this. The K value for water is given as 1.86 degrees Celsius per molality. The molality can be determined from this. But watch, I'm going to build the I into this while I calculate the molality, because I know that it's a strong electrolyte and that it's a colligative property. It's a strong electrolyte because it starts with a metal. So this is going to be made of 3 pieces of Na+ and 1 piece of PO4 3-. But that is 4 ions. So when we take our molality, which is usually moles of solute, in this case that would be 0.10 moles of Na3PO4, we usually put that over the kilograms of the solvent. So let's go ahead and do that. You'll notice that I've got this over a 1 for right now. The solvent is here, 525 grams, but it needs to be kilograms of just the solvent. That would be 0.525 kilograms, in this case of just the water. You should be able to prove that that's the right number because 525 grams divided by 1,000 grams is 1 kilogram. So that proves that this is the right value. And now for the new part, because we've done things like this part already, but I'm claiming this is a colligative property and it has ions. So I'm going to add the term that for every 1 mole of Na3PO4, for every one of these formulas, you get 4 moles of ions. This is multiplying it by the I value of 4. 4 over 1 is 4. This is times I, times 4. I've just pre-built it in. At this point, I now have the correct delta T because I've got an adjusted molality, not the original definition, but an adjusted one. And we'd always have to do this for the colligative properties. We can do this calculation, 1.86, you should do this at the same time, times 0.1 times 4 divided by the 0.525. You should be able to verify that this is, to 2 significant figures, negative 1.4 degrees Celsius. Molality cancels and degrees Celsius is remaining. This is the delta T. I know it's negative because I know freezing points go down and boiling points go up. Since this asks what is the freezing point, we would remember that water has a freezing point of 0. We would look up a solvent that we don't know, but we're supposed to know water boils at 100, water freezes at 0 Celsius. So the new freezing point would simply be the old freezing point, 0 degrees Celsius, minus this delta T, which we just got, which is easy math. The freezing point is in fact negative 1.4 degrees Celsius. That's convenient because it's water. But I could do it with another value that had something other than a 0. This takes care of the effective concentration part. Make sure you see how this functions. Now we can go to a secondary part. It is true that every colligative property can be used to determine an unknown's molar mass. We should have a strategy for this, so I'm going to show you what that strategy is. I'll finish erasing shortly. But every colligative property, each one, there are 4, each colligative property can be used to get the molar mass of an unknown. Now, if it's not an unknown, we don't need this. We would just add up the formula mass from the periodic table. But if we don't know it, then we have to use the idea that the units of molar mass are grams divided by moles. And the units are an equation. If you know the grams and you know the moles, you can tell me the molar mass. So let's see what the strategy is for each colligative property. I can delineate it here. Number 1, we would use the colligative property to calculate a concentration. Once you have the colligative property concentration that you can get, then number 2, we can use the concentration that we just got to calculate moles of the unknown. Once you calculate moles of unknown, you will find that you have everything that you need because you can put the grams and moles of the unknown together. Let's take a look at how this strategy is used. I can clear off this part of the table now. If you need to, you should be able to rewind or pause the video so that you can see what was written. If I've erased something too quickly for you, that would be fine. Let's go back to your handout then. Example number 9 lists the following information. It has more than this, but this is the information that matters. There is 2.05 grams of something called polystyrene. They put it together so that they make 0.100 liters of the solution. After they do that, the osmotic pressure, which is pi, is measured to be 0.0119 atmospheres at 298 Kelvin. Then the question claims we should be able to say what is the molar mass. Well, this is not a problem if you will remember, and you will have to remember that the units of molar mass are the equation, and you have to know the units, which are grams per mole. So you are going to need the number of grams of the polystyrene at exactly the same time that you know the number of moles of polystyrene. Well, we can already do one of those right now because the problem gives us directly 2.05 grams of polystyrene. I'm jumping to this part because that's always given in the problem. You can measure it. You put it on the balance, you measure the grams. So we have 2.05 grams of the polystyrene. We're almost there. If we just knew the moles at the same time, we could answer the question, and I'm claiming I can do that. I can calculate the concentration from the colligative property, and then I can use the information in the problem with the concentration to get the moles of the unknown. So let's do that. This is about osmosis. It says it's the osmotic pressure. There's only one law for that. Pi equals m times r times t. Well, in this particular case, we would always be given r. T is given. The pi is given in the problem, the osmotic pressure. So the unknown is the molarity. So I would say, if you can't remember what to do, solve for the thing that you can get. We can plug in all the pieces we need. Remember that you have to play by the rules. You have to use the units that are on the value of r that is given. So in this particular case, the molarity is not known. We would look up 0.08206 liter times atmosphere divided by mole and divided by Kelvin. Remember that would be given. Then the temperature is 298 Kelvin. I can put that in because Kelvin matches Kelvin. And the osmotic pressure is given as 0.0119 atmospheres. I can put that in because it matches the units that are given. I can solve this directly because everything matched. If the units didn't match, I would convert them and then plug them in. If I divide both sides by 0.08206, on the right-hand side, these will cancel to make a 1, but I'll have to do that over here, 0.08206 and 298. If I do this division on this side, on the left side, I will get the value for molarity. So you should be able to do that at the same time, 0.0119 divided by 0.08206 and also divided by 298. You should verify that you're getting 0.0004866. It keeps going, but I only have 3 sig figs. I'm going to keep the full number on my calculator. Now remember what the units are of molarity. The units of molarity are moles per liter of solution. In other words, this number that I have right here has units. The units are moles of the polystyrene, the solute, divided by 1 liter of the solution. The molarity value that I just got is in fact a conversion factor. So I just did the first part, I got the concentration, and now I'm claiming if I go back to the problem, I should be able to start with something I haven't used, use this concentration value now, and get to moles of unknown. Look over here. What have we already used? I used this, I used this, I used this. I won't use those again, but I haven't used 0.100 liters of solution. If I will start with that, 0.100 liters of solution, can't I use the conversion factor I now have? The molarity is a conversion factor, and it can be used to give me what I need. Supposedly, I need the moles of polystyrene, so we can do it. I'm going to put this molarity here in blue so that you can see that the units cancel. 1 liter of solution has 0.0004866 moles of the polystyrene. And of course I can do that. That will now be 0.0004866. I'm going to use the full number. I'm going to do this calculation. I have this full number on my calculator. These are the moles. Look at what we did. We got a concentration. I used the concentration to get just the moles of the unknown. And now I should be able to put them together, and I can. I'm going to drag this number over here, 0.0004866. Again, I'm using the full number. These are moles at the same time as grams. If I do this calculation and round to 3 significant figures, you should be able to prove, you need to prove that the value for the molar mass is 4.21 times 10 to the positive 4th grams per mole. This is the molar mass. It's a large molar mass because it's a polymer. Polymers are big fat things. They aren't able to get molar masses by a formula because they keep going, and so you have to make it and then prove what its molar mass is. This is one way to do that. Hopefully you see how to do this. We should be able to do this on any of them. You're doing a lab that uses freezing point to do this. So I'm going to do examples that aren't freezing point, but you need to practice the lab that does use freezing point. So let's do example number 10. I can put the pertinent information here while you can write down this. So the information from number 10 says there's an unknown, and 35.7 grams of the unknown is dissolved with 220.0 grams of CHCl3, and this has a boiling point of 64.5 degrees Celsius. It then asks me, what is the molar mass? It has to give me some more information. For instance, the boiling point of CHCl3 normally, when it's pure, the boiling point is 61.26 degrees Celsius, but this has changed. So the boiling point of the pure is not the same as the boiling point of the solution. And then it also has to tell me the Kb for CHCl3, which is given as 3.63 degrees Celsius per molality. So this information is all given on the handout. But notice that the structure of the beginning is entirely the same. It says what's the molar mass. What's the molar mass is going to have to be the units of molar mass. It's going to have to be the number of grams of the unknown divided by the number of moles of the unknown. And once more, the grams are already given because you can do that easily. You put it on a balance. So we currently have 35.7 grams of the unknown. It will always work that way. I have already used it. I'll never use it again. What I need is the number of moles. All right, I'm going to back up to the strategy then. Supposedly this is a colligative property. It should yield a concentration for me. Once I get that concentration, I can use it as a conversion factor to get to the moles of the thing that I'm missing, and then I can put them in and have the answer. So let's go ahead and write down what we have for this example. This is not like number 9 in this case, because number 9 was osmosis, and the osmosis law is different from this one. This colligative property is boiling point, and we know that boiling point is elevated. Remember, there are 4 colligative properties. You should know the equations for them. Vapor pressure lowering has an equation. Boiling point elevation has an equation. Freezing point depression has an equation, and osmosis has an equation. You have to have them memorized so you can do the problem. Boiling point's equation is that the delta T of boiling has to be the K of boiling times the molality. Well, we'll have to do a little bit of work. The boiling point is given originally as 61.26, but the new boiling point went up. Well, that would give me delta T. In fact, we can get that right here. 64.5 degrees Celsius minus the 61.26 will give me the delta T. How much did it go up by? So 64.5 minus the 61.26, you should be able to do this at the same time, gives us that it rose by 3.24. And I'm going to have to stop at the ones position. There's really only two significant figures here for delta T. All right, we can put that in. 3.24 degrees Celsius. The KB we would look up, but it's given in the problem. In this case, 3.63 degrees Celsius per molality. And then the molality is unknown. Well, if the molality is unknown, you can solve for it. In fact, don't forget that that's always the general idea. I have enough information to get this. I can find that. The one that's unknown, I would solve for. Well, everything matches. Degrees Celsius matches. If I just solve right now, I'll have molality directly. Dividing both sides by 3.63. You should be able to prove this side cancels to make a 1. That the molality is going to be 3.24 divided by 3.63. And in this case, this is claiming that the molality is 0.89256. There's only two significant figures in it for real. The units of molality are moles of the unknown. Remember the units of molality, just like the units of molarity. The units of molality are moles of the unknown divided by kilograms, 1 kilogram of the solvent. Now, 1 kilogram of the solvent is exactly the same as 1,000 grams of solvent, so I'm going to choose to write it this way. For every 1,000 grams of the solvent, there has to be this many moles. This is the molarity. It's the molality, not the molarity. Now I've got the concentration, and I can use the other piece of information in the problem I haven't used to get the moles that I'm needing. So going back to here, I've used the boiling points and the K. I have not used that there's 220 grams of the CHCl3. The solvent is CHCl3. Well, then I can use this at the beginning. So 220.0 grams of the CHCl3 is given at the start. And we just got the molality as a conversion factor. For every 1,000 grams of the CHCl3, there must be this number, 0.89256. It keeps going, 2 sig figs, moles of the unknown. Well, we can do this division. So we have the number still on our calculator. So that number times 220, and then divided by the 1,000, is claiming that there's only 0.1963 2 sig figs moles of the unknown. But I can move that over here because it's the only thing I'm missing to solve the problem. If I do this division and round to two significant figures, I will have the answer, which is 180 grams per mole. You should be able to prove that that is in fact what we have. So colligative properties are powerful. Make sure that you can do this type of work, that you see how this strategy works. When you practice lab, make sure you practice it from this perspective also. Start with the data from lab, the freezing points that are known in the information at the start, and then practice this as a way to get the correct answer for your lab. Now, this closes 11.4, and it allows us then to finish 11.5, the last part of the chapter. Well, 11.5 is reasonable to read. You should read it on your own, and it is about colloids. The whole chapter is about solutions, and colloids are close to solutions, but they are not truly solutions. So you're going to have to make sure you see how they are different. I'm going to try to show you how they're different, but I will need you to read the section to make sure you get all of the details that in fact you would need. It will help us if we talk about normal solutions and normal things that are not solutions. What I would say are suspensions. Suspensions are exactly the same thing as when we would say that something is cloudy. So something like mud that is cloudy but then settles out over time is a suspension. The particles aren't dissolved, they're just held up for a bit in the water and then they sink down. Whereas a solution is not cloudy, it is clear. If we make a contrast between these two things, then we can put colloids in the middle and see how they compare or are different. So, for instance, solutions are by definition homogeneous mixtures. Whereas suspensions are heterogeneous mixtures. So this would be a beginning definition. Another thing we could say for something to be a solution, the solute would have to be the smallest particle of solute. I have to use the generic word particle because I don't know what solute I'm talking about. It could be atoms if it were made of an element. It could be molecules if it were a covalent compound. It could be ions if it were an ionic compound. I just don't know, so I can't say better than this. Whereas a suspension, you have large clumps. I'm not going to call it a solute because it's not actually dissolved, so it's not a solute. But the things that would be trying to dissolve are just in too large clumps. Another idea here, solutions do not settle over time. They do not settle out, whereas suspensions always will. They do settle over time. They settle out. They'll fall down. Another thing, I cannot filter something is actually truly a solution. You can't get those particles, you can't filter with filter paper, whereas these, you can filter. Now, let's talk about colloids, which I haven't put in yet. If we were to meet a colloid, I'm going to claim that it kind of lives in the middle. If we were to look at it, it looks clear, generally speaking. Now, maybe there will be some examples that won't, but most of the time, if you look at a container that has a colloid, it won't look like it's cloudy. It will look clear under normal circumstances. However, the size of the clumps are not the smallest particle size. These sizes of clumps are between 5 nanometers and 1,000 nanometers in diameter. You want to know approximate range, so 5 nanometers to 1,000 nanometers is significant size. If I would wait for them to settle out, they do not settle out over time. If you try to filter them, you usually cannot filter. Notice how things are similar and how they're different. It really looks like a colloid, by most experimental ways of looking at it, looks like a solution. However, because the particles are not the smallest possible particle size, you should not call it a homogeneous mixture. It is not. It is a heterogeneous mixture. Make sure you label it that way. Only solutions are homogeneous mixtures. So, if they're so similar to each other, how are they going to ever be different? Well, it turns out that there's one thing that will show the difference between a solution and a colloid, other than trying to find a way to look at this. You can't see the size, generally speaking. So, the way that we can see this is that a solution does not scatter light. What do I mean by scatter light? Well, if this is a container that has a solution, and you shine a beam of light. So here's my representation of a flashlight. And if I send a beam of light through a solution, that beam of light will pass unimpeded through the solution, and you will not see the beam of light. You only see things where your eye sees the light. So unless I put an eyeball over here to have the beam of light hit it, you won't see it. If I stand perpendicular, you can't see a beam of light going through. It's not scattered. A colloid, on the other hand, does scatter light. And in fact, this scattering of light, so it does scatter light. This scattering of light has a name. It's an effect. It is called the Tyndall effect. The Tyndall effect, which scatters light as light goes through, is the way I can easily tell a colloid from a solution. So here's the difference in the picture then. So if I have a colloid here, and I shine a beam of light at it. Here's again my flashlight. It's a great drawing. As the beam of light travels through, if I have my eye out here, like over here where I didn't see this, what will happen here is that the beam of light will be scattered perpendicularly, up and down and out and behind. It will be scattered all along the way. Well, if it is being scattered perpendicular to the direction it was traveling all along the way, what you will see is you will see this part hitting your eye, which is out here. So when you can see a beam of light, even when the beam of light is not pointed at your eye, then that is showing you that there is a colloid. You could look in your textbook at figure 11.31 to see examples of this, but I think you can think of some right away. Sunsets, when people are like, ooh, that's a pretty sunset. Often they're looking at a colloid because they see the beams of light going through the air, and the beams of light are showing, they're doing the scattering, which means the air up there must have a colloid, probably water droplets in it. Or if you have a fog machine at a concert, you can see the beams of light from some sort of laser show. You would never see them if you didn't have the fog, but because the fog is a colloid, you can see the beams of light going whatever directions they are, even though the lasers aren't hitting you right in the eye, which actually sounds relatively painful. So make sure you see the distinction, read more. You can read the text for examples of other types of colloids, but the Tyndall effect, the scattering of light, is the easiest way to tell if something is a colloid. With this, I want to do one last review. We do have a quiz next class time that will be over chapter 11, and you should remember that you are required to know how to do both type 1 and type 2 and type 3 problems, my own designations, right? So let's say that we have one of those that we ought to be able to practice. So let's go with an easy one. Let's go with, what if we had a solution that is 19 molality, CH3OH, and it's aqueous. If someone were to give us a 19 molality solution of CH3OH in water, aqueous is in water, then we could ask the question, what is the mole fraction of CH3OH? And we might as well ask, what is the mole fraction of water at the same time? So I'm doing a type 3 problem. Remember how we could tell. A type 1 problem is when all you're asked is to calculate the concentration. A type 2 is when you are given a concentration and you use it as a conversion factor to turn something into something else. We've already been doing that with the previous colligative property examples. I was using a type 2 strategy after I got the concentration value. I then used it that way. So I'm going to exercise this, which is a type 3. By my designation, I can tell it's type 3 because I'm going from one unit to a different unit, from molality to mole fraction in this case. Okay, well, the easiest way to do this type of problem, the best way to do it so that you know that you're getting the right answer, is to quickly make a picture. You do not have to have good art skills the picture's purpose is not to show a lovely picture, although you can draw as nice pictures as you want. It's to arrange the information so that you know how to work with it correctly. So we have a solution of CH3OH in water. So here is the CH3OH, and when we put it with water, that makes it aqueous, and then here's our solution. Because I was given molality, I'm going to assume that there is 1,000 grams of just the solvent water. I'm assuming that because for molality, the denominator is kilogram of solvent. Water is the solvent. So if I had 1 kilogram of water, that's the same as 1,000 grams of water, then I could say how many moles there are. The number 19 would have to be the numerator. I would know I had 19 moles of CH3OH for every 1,000 grams of water. In fact, let me put that over here. Remember, we have a framework that is implied. The framework is grams and moles, and then I can have volume if I want it. I know that grams are additive, so that this plus this would give this. I also know that moles are additive. I'm aware in my framework that I could connect here to here if I want, but that there is no connection here. And I know that there's a volume over here, but in this case, I know I'm not going to use it because there's no density. I don't have to draw the whole framework. Generally speaking, I can just draw the parts that I need. So in this case, I have grams of water. I just assumed 1,000 grams of water. Because if I assume that, then there would be 19 moles of CH3OH. Because 19 moles divided by 1 kilogram is 19 molality. You could do other values, but you would have harder math. So this is fast. Now, once you've done that, then you would ask, well, what is needed for these? What is the equation for mole fraction of CH3OH? Well, that's actually not that hard. Mole fraction is what it sounds like. The mole fraction of CH3OH would be the number of moles of CH3OH divided by the number of moles total. They also ask for the mole fraction of water, but that has exactly the same pattern. Mole fraction of water is the number of moles of water divided by the number of moles total. So if I would take my picture, which is currently true, and drive to the point where I have these pieces of information, I would have the answer I want. So we can do that. I already have the moles of this. I'm going to need the moles of water so that I can get mole plus mole to give me total moles. All right, well then this is not a problem. We can show this work here. I need to have 1,000 grams of water. And if there is 1,000 grams of water, you can add up the 2 H's and the 1 O. Look at your own periodic table. There's 18.016 grams of H2O if you add 2 H's and 1 O for every 1 mole of H2O. If we do this division, 1,000 divided by 18.016, I have just generated that this is 55.50 moles of water. I have at least 4 significant figures here. I think I have more, but I'm going to be restricted in the end to 2. If I do this addition, so adding this number that's saved on my calculator, I'm going to save it first. If I add it to 19, then the total moles is going to be 74.506. I'm going to save that number as well, but by addition, I can only go to the units position. All right, now I have the picture generated. I traveled as far as I needed to answer the question. I have the moles of CH3OH, 19 of them. And then I have the moles total, which is here, 74.506 moles total. There's only 2 significant figures allowed. I have the full numbers on my calculator. I'm not rounding them until the end. So doing this division, you should be able to prove that this is 0.26 mole fraction. Now the other one, since they asked for it, I can give it to them. I have enough information in the problem. The moles of water is right here. 55.50 moles of water. I can only go, well, I can go probably 4 positions. Again, it doesn't really matter. The periodic table mass is restricting me. I'm going to be restricted, though, by the denominator, 74.506 moles total. This only goes to 2. If I put these pieces together, and again, I'm going to use the non-rounded numbers, I'm going to pull back the water value and then divide by the total number that I had saved, I'm not surprised that it's 0.74. This is my last point about this. Make sure you can see how I moved through this, but it was nice. Since they asked me the mole fraction of 2 things, and there's only 2 things, notice that mole fraction of one plus the mole fraction of the other had to add up to 1 total because I calculated everybody. I actually didn't need to do this work down here. I could have said 1 minus 0.26, and it would have told me what the mole fraction of the other one had to be. All right, with that, make sure that you see how to do these types of problems, that you finish up chapter 11 so that you're ready for the quiz that will come at the start of next class time.